So we'll take a break and we'll meet after that. So let's kind of resume. Okay. So now earlier, so when I was talking about kind of the CLB and all, I was saying that we have an LUT and this carry chain logic, right? So now I'm just changing the definition that okay, now the CLB contains what is known as slices, and now the slice contains the k input whatever that LUT and the carry chain logic, okay. And now we can have multiple of such slices, and here we are just showing one configuration where the CLB contain 2 slices. So now what you can think of is that k input LUT, the carry chain logic which I showed up front with the flip flop and all, so that is part of your slice, okay. Now we look at one of such kind of slice, okay. Again so this is from Xilinx and maybe kind of a bit old, it's easy to understand, but the same kind of explanation can also be kind of carry forwarded to maybe the vertex 5, vertex 6 and any other, let's say the FPGA. So once we understood this one by looking at any other the slice diagram and all, so we should be able to understand, okay, good. So now I'll just give let's say few minutes to also have a look at it on your own, okay. What we have is that if you look at maybe this slice, so we have let's say this f, let's say variables, right? We have f1 to f4 and we have this g1 to g4, on the top we have c1 to c4, these are all kind of input, and now we also have this kind of a k, and now if you look at the output side, so we have a y and yq and then x and xq. Now let's try to understand, given such a kind of the slice, what we can all really do with it, okay, good. So here, okay, I'm just trying to let's say show you one use case where 2 4 input functions are registered output functions and 1 2 input function can be implemented, right. So let's try to understand what I'm trying to really say, okay. Now so we have let's say this LUT, right. So how many inputs for the LUT? We have 4, right. So that means it can implement any 4 input function, okay. So similarly if you look at this G1 to G4, right, again that is 4 input LUT, right, it can also implement any 4 input function. Now let's say I wanted to simply take that out, okay. So I can just route it from here and through this wire, and of course this is a multiplexer, right. Of course let's assume that the select signal is such a way that it just goes and then connected to maybe this D input, right. And again you see, right, so again this let's say f function which is implemented here, if needed it can also be sent it. 2 4 input functions, registered output functions, that means it can be registered, right. So that means it goes through the flop, yeah, good. And then now here let's look at maybe these variables, okay. Now we have one more LUT here, okay. So here this LUT, so now one input can come from let's say here we have a C1 C2, right, okay. Maybe this was correspond to C1 and this correspond to C2 and C3, let's say, okay. So C2 and C3 can just come here through these muxes, and then I can implement, so now the 2 let's say variables are coming, right, okay. I can also implement so 1 2 input function with combinational output, of course, right. Once I registered this one, these flip flops are kind of used, I can only just simply send this out. That means so given this let's say kind of a slice, I can implement 2 4 input independent functions, that output can be registered, and I can also implement 1 2 input function, okay, good, with a combination output, okay, good. Now for instance let's say I can also do the same thing in a different way, or I can also implement something different. Now I have let's say 5 input function, can I implement? The answer is yes, but of course, right, so it has to be only combination. Now let's say just now we discussed, right, this the Shannon expansion theorem, right, what we discussed. So we can kind of express any function with less variables, right, if there is a 5 input function, right. But of course I do not have a 5 input lookup table. What should I do? What should I do? I should use maybe Shannon expansion theorem, and I have to cofactor it with respect to one variable. So if I cofactor, let's say and then all the cofactors are 4 variable functions only. That means what I can do is that, so positive cofactor I can implement here, the negative cofactor I can implement here. Okay. So now fx is coming, fx bar is coming here, and now one of the input is there, I can bring x. Now x I am combining fx and fx bar, right. So now total fx is a function of 4 variables and x is there, total 5 variable function. Now, so the idea is that I can implement 4 input functions, or I can also implement 5 input functions, anything is possible. Okay. But now in case of this 5 input function, I will not be able to kind of register it, right. So I just have to, because there is no path from this multiplexer, it just has to go out. But in the 4 input case, I can also really register it, that means it goes through the flop, right. Okay. Now all these let's say possibilities are there, and depending upon what we wanted to do, we can use the logic. Is that clear? Okay, good. Now let's try to do this example. Okay. So I mean, some function is given, right. This is what actually, right. So when you write a Verilog code or anything, internally the tool will come up with such expressions. So we'll see that on definitely on Friday. Yeah. Okay. Now x is a function, is a function of 4 variables, a b bar plus c plus d, and y is a function of, again there's something called a, k, and again c, d, and a is l. Too many variables are there. Okay. Now we have to implement this function, right, using let's say this slice. Okay. How do we really do that? Any ideas? So now let's look at x, right. X is a function of how many variables? I mean, you see, right, we are not worried about the function, we are just worried about only the number of variables. If you see, right, once the function is, right, we are just going to write the truth table and load the content, right. We doesn't really care about what goes inside the, let's say, the LUT, right. So now we are concerned only with the number of variables. X is a function of 4 variables, right. What I can do is that I can implement, so now we looked at let's say the upper, let's say LUT and lower LUT, right. I can use one of them. Okay, good. How about y? How about y? How about y? So x, right, x is a function of just a, b, c, d, right. I said it's a 4 variables. Okay. How about y? Okay. Now if you look at, right, I will do something, I will take this k common, a plus b, c bar d bar, right, into k plus aejl. Again, if you look at this aejl, right, is a function of 4 variables, right. So I think again I need one LU to implement it. But now if you look at this one, so what is x? What is x? A bar, b bar, c plus d, right. Right. So by looking at this, let's say x and this y, what can you say something? Y equal to, I can say, if this one and this one, what is the relation? Inverted, right. It's a x bar k. Okay. Now if I implement somewhere, I will just simply call it as a function p. Now f is a function of x, k and p, right. So somehow we have to implement this thing. So how do we do that? We will see. Okay, good. Now as I said, if x is a function of a, b, c, d, right. So what I am trying to do is that I am trying to really use sorry, this one. Yeah, that's okay. Fine. Yeah. Okay. Right. So x is a function of a, b, c, d, right. So I am using this, let's say lower, let's say LUT, and I am generating the x here, right. So what I will do is that this x, I will just as output, right. I will just use this path and send it out. Clear? Okay. Good. Now I have this aejl, right. Okay. I am using this upper LUT, aejl, right. So what could be the content here? All zeros, only the last row is 1, right. It's AND gate, right. So what is the content inside? Just 1, the last row. So now I am implementing this AHL. Okay. So now I have this P and I have X. Now you see, right, I do not have to worry about. So now I have, let us say, P and I have, let us say, X. Now if you look at the Y is a function of what? This, let us say, AHL I am calling as a P, right, and then function of X and K. So somehow I need to get a K, right. So what I will do is that, so I will get a K from one of these inputs, right. So now you see here, and now the Y is a kind of a pure combination, right, it is not a registered output. Yeah. So now, right, I will use the K here. So K is coming from here. So I got this P, which is nothing but AHL, that is one variable now. Once it is implemented, it is one variable for me, right. It's a K is a function, means like AHL, right, I am representing with a P, and now this final Y is a function of X and K and P. Just, so again I have 3 input lookup table, right, I am just giving to them, and then it is implemented here. Okay, now this is what the synthesis tool does. You give any Verilog code or anything, ultimately we have to come up with this equation, and given this logic, okay, we have to optimize and then implement it. Okay, now I mean these are kind of simple circuits, right, so we can do with a pen and paper, but of course, right, so we have to really automate this process in the tools, but essentially the tool exactly does these things. Okay, good. So let us move on. Okay, so what do you do now is that, so I gave you one sheet where the 2 similar circuits are printed, exactly these circuits. Yeah, you can use one of them. So you can use one of them. If somebody needs the sheets, so they are there. So where this slice is there available with you, in one of the sheets, this slice is available with you. Now your job is to really think about this, let us say, circuit. Now, so given a logic functions, we did it, right. Now think about this logic. Okay, what comes out of this logic as the expressions and all, right, and then that expressions we need to implement on given slice. Okay, so try on your own. So the sheets are there. Looking at the combination logic. So now here we have maybe so right, so Z equal, right, Z of course, right, this non-block statement is there. This is going to be your combination logic. This whole expression is going to be combination logic. Okay, and then of course, right, that we need to assign it to Z. Definitely Z is going to be a kind of flip flop, and the same explanation which I gave you earlier, right. So here, which is your clock pin? I mean, right, I mean, yeah, I mean clock pin is there. To that clock pin, which is going to connect it? B, right, very good. So which is a reset pin? A. Now you have it, right. So that means you can really expect that in your design there is a flip flop where the reset pin is connected to A, right, and the clock pin is connected to B, and there is an enable pin, right. Let us assume there is a flip flop with enable, right. So the enable pin is connected to what? Done, right. And now what goes to the D? This whole expression, right. Okay, now you need to think of how do we really implement this whole expression. Right. So on the first, I think, yeah, I mean any of the examples you can take and also solve that. Okay, so we have a design called 8-bit, let us say, adder circuit. Okay, you can think of it's a carry propagate adder, or carry look ahead adder, yeah, and implement that also using that given slices. So we can again take 15-20 minutes, not an issue, right, using that LUT, and then you have to also realize your D flip flop. So maybe if somebody need help, maybe we can do it a bit later, but with the interest of time, so let us continue. Okay, so maybe I am there, after that we can just sit and work it out. Okay, let us just I think we need around 15-20 minutes, so fine, good. So now in the past slides, right, So what we are trying to really show is only this part of the logic. So that F and G and H, right? But again, as I said, right, the slice also will have this, kind of this carry chain logic. Okay. So that, even, visible in one of the example, right? So as I said, right, so when we are not really kind of, when we wanted to really implement address and all, it's better to use this kind of a carry chain, kind of a network. Okay. Now, if we show everything together, right, so it kind of a bit clumsy and, we won't be able to understand. That's the reason we are just trying to show in bits and pieces. But this carry chain logic is also part of the slice itself. Okay, good. Now, now let's say we understood, kind of the CLB. So now let's try to talk about this programmable interconnect points. Okay. So now this configurable kind of a routing network on FPGA is accomplished using what is known as this programmable switch. Okay. Now what is a simple model for the switch is that, use an NMOS transistor. So what is shown here is that, okay. So let's say there is a memory kind of a SRAM cell which you can really program to either to 0 or 1. Then what happens is that these 2 points are really connected. If this is 0, so that's not connected. In a simple way, we can really achieve these 2 connections. Okay. Good. So here, so there is something called 6 point, 6 position cross point, or some, the switch. Okay. Here, let's say if there are 2, let's say wires which you wanted to connect. So this one switch is enough. You can think of this, let's say, circle as one transistor which can be programmed to 0. But now if there are 2, let's say, intersecting lines, yeah. So then, so we can also have something like this. But now if you look at here, right, so this signal from here can also wanted to go, I mean, if you say this is east, so we wanted to go to, north also, or if we want to go to south also, or maybe this signal wanted to go up, right, I need to connect, let's up, and of course this signal wanted to go, to the east side, so I should be able to connect, and again, so this let's say north signal wanted to go to east side, so all permutations and combinations are needed. So that's the reason if you look at here, right, so we have this 6 point cross switch. So right here, of course, right, so anyway this connection is possible, this connection is possible, and we are trying to really show that. So from, let's say, west to, let's say, south, it's also possible, from east to north this is also possible, right, and similarly like from east to south, and we can say it's a west to north is also possible. So now whenever we say this, let's say, kind of a CLBs, and then we are trying to really show this kind of a switch matrix, right. So now wherever the lines are there, we can think of there is this 6 point switch, and now again the 6 point switch, right, how many switches we have, that many kind of transistors we have, and that many SRAM cells we have which will get programmed. Now you can think of, right, as I said, when we are mapping the logic to the FPGA, what we said, we have to generate the content for the LUTs. So the LUT content is nothing but the function truth table values, right, that we have to program, and similarly that bit file also consists of the configuration for these connections, right, in simple way, right. So here, I mean, when we talk about this FPGA interconnect, there is something like, the single lines, double length lines, and long lines. So this we can really kind of give an analogy, right. So if you look at any kind of a major city, right, so you have kind of a local buses, right. So what is the point, what is the use of them? I mean, they don't go outside city, and they have the point to point. And similarly we have buses which just from the city maybe just go little bit outside, the region, or the simple towns. And there are some buses which they do not really kind of go to this simple towns, or but it's a intercity, right. They are really long, they will not stop in between and all. The same concept here. So the single lines are, okay, so maybe I'll show you here. Okay, so if you look at the single lines, right, so again sometimes these are different sources, the slides are the figures are copied. So this PSM is nothing but a switch matrix. Now if you look at the single lines, right, so one switch matrix to the next switch matrix, they definitely connect. But now if you look at this double lines, right, okay, now if you look at, right, so this is going here, but now it will skip the next one, this one, right. So similarly, I mean, there's a quad lines and octal lines, they will skip maybe 3, let's say, switch matrices in between, 7 switch matrices in between. The reason is that, so if it is a long line, so I will do that, I mean, I think, so those who have done the VLSI design course, they might be kind of aware of this, right. if there is a kind of a signal you wanted to send it for a longer distance, so the routing of that, right, so metal width and all we use bit longer, because it's going to a longer place, of course, right, the current carrying capability or the resistance should be minimum. So the longer lines, the design should be something different from the single lines. That's the basic idea. So now, so we can think of that FPGA really consists of these single, double and these long lines. So not only that, of course, right, so for the clock distribution and all, right, so we should also have some kind of a global, let's say, nets. So that are also part of your what is known as clock management tile. Okay, that's what we have here. So for instance, so what we are trying to really show here is this is your, let's say, FPGA. Okay, now I mean these are the pins where, let's say, clock get connected. So now if you look at here, right, so these are kind of a primary global nets. So with the clock or reset, right, these are the global signals which will go to each and every flip flop. Now right, so now they come, let's go to the middle of the chip. Okay, and now we have kind of this distribution lines. Now if you see here, these are the secondary lines which are getting connected to these primary lines. Okay, now these secondary lines will be kind of used to distribute this clock and reset to maybe this local CLBs and everything, right. So again you can think of this is implemented bit more complicated when in the latest FPGAs. Okay, so we have what is known as clock management tile and all. Okay, good. So now, so far we talked about CLBs, this kind of switch matrices, and the last point is, right, so FPGA said which also contains the IO blocks, right. So of course, right, to read the signals from input or maybe send the signals output, so we need to have this, let's say, input output blocks. Again it's a very simple. Suppose, so on this side you have an FPGA and you wanted to really drive a kind of a pad. So now, so here we can take this signal, we can also register it and then drive it or directly drive that. Okay, whenever you are driving, as I said, right, we need to have a buffer. Okay, the signal goes out. Okay, and now if you wanted to really read in a signal, so of course input signal is connected here. Okay, now through this path it will come, we can directly take to the FPGA or we can also really kind of register and then take it inside. Okay, so basically, right, so we can use each pin for the input or output, but again as I said, so one of them will use and accordingly will enable the output or input paths. Okay, and of course, right, we can also really kind of do the feedback also. Good. And now this is a kind of a simplified view, and for this XC400, I mean the same thing, but there are like more components, but essentially the functionality is exactly the same. Okay, good. Now, so I mean that XC400 I showed, right. So now the other class of FPGAs are there. I mean, so that architecture name is Vertex. Okay, so again, so those architecture really look like this. So we have this one CLB, and again we also have something similar, but again the names could be really different. So again this is a kind of a very simplified view, and if you look at one of the slides, so it will look something like this. So this is kind of a bit quite different from, little bit different from what we have seen before, but this is a Vertex 5 kind of a slice, one of the slice. Okay, but again you see, right, so by looking at this diagram, so we can simply say that, okay, so this LUT, if you implement, of course there are 4 inputs and all, so we can check. So the middle part is your carry chain logic again, right. So now, I mean with this understanding, you can open any of the, let's say, the Xilinx documents, even Vertex 5, Vertex 6 and Vertex 7, so you should be able to really understand the logic. Okay, good. So now what we are trying to really show in this diagram is that, so this is a kind of one of the modern FPGA, so where we are trying to really show this kind of logic cells. So that is where we have this LUTs, CLBs and everything, and now we have this block RAMs. As I said, right, if you need a dedicated memories, as I said, why not integrate them in the FPGA itself. Okay, so that's what we have, these block RAMs, and then we have these DSP slices, right. As I said, there are some multipliers, and as I said, right, so we will make this dedicated, let's say, the multipliers, and we will also give them on the FPGA. And now if you, let's say, write a code in a Verilog where you use a star for the multiplication, I am going to use one such, let's say, DSP, let's say, unit. Okay, and then, so earlier I showed for the distribution of the clock, right, so there is a effect, this red color one, some kind of a clock distribution circuits. Okay, so they will try to minimize your skew and all. Okay, and again you said we can go into the details, but so for this class it's not really necessary. And then we have this I/O, and not only that, so there are like serial communication, right? So specialized interfaces, PCI, SPI, everything we can also have. So the modern FPGA has all these things. Okay, good. So now, so we talked about the block RAM, right? There's something called a concept called distributed RAM. Okay, now let's assume that, so let's say the block RAM is not available. So now you wanted to implement, let's say, a small memory. How you are going to implement it? The question, right? So now what we can really do is, so if you look at, right, the architecture, we have an LUT, right? So LUT is realized using memory, right? So that means, suppose we have this 4-bit LUT, right? So now what is the kind of size of this memory? It's a 16 locations, right? And 1 bit is, right? So that means it's a 16-bit. So now if you wanted to really realize a 16-bit register, I mean I can also really go ahead and do it, right? So now if I wanted to use a kind of a 32 cross by 1 bit, let's say memory, I can use 2 of them, right? Okay. So once if I have let's say 2 of them, I can also say that it's a 16 multiplied by 2 also, right? So this is implementing 0th bit position, and this is implementing 1 bit position. So I can also combine such LUTs, and then I can also implement 16 locations, maybe 8 of them I can combine. So 0th bit, 1 bit, 2nd bit, and I can go extend it, right? So now why we call it as a distributed, because these LUTs are not together, right? They are distributed all over, right? So now the memory which is implemented using these LUTs, we call it as distributed memory in simple, right? The earlier, right, so the block RAM, it's a dedicated RAM, it's available in a special row, right? That's a dedicated row. But here this, let's say RAM, let's say this RAM, it's distributed all over your FPGA. That's the reason we call it a distributed. So for implementing simple registers and all, so we can really use it. But again, if you need a kind of more memory size, it's always better to use the block RAM. Okay, good. So now I was talking about the DSP slice, right? Again, so this is one such, let's say DSP, let's say tile. So now in this tile, so we have again 2 slices. Okay. So now each slice will look the same, and now if you now try to look at here, right? So we have these different inputs. So looks like we can really perform 25 by 18 multiplication. One input could be 25 bits, and another input could be 18 bits, and the whole multiplication we can really do it. And now if you look at here, right, so we can also add them or subtract them, and whatever this add and subtract this, right? So if you look at it, I can do a plus or minus d multiplied by b, yes or no? And now this is a kind of a dedicated block, hardwired, which is instantiated. So similarly I can also do some kind of a bitwise comparisons and all. So basically whenever let's say, as I said, the kind of additions and dedicated multipliers are used, so this DSP tile is going to be used, right? And again, as I said, right, so if you have more number of these DSP slices, that FPGA is going to be a bit expensive. Okay, good. So now, so far let's say we looked at the FPGA architecture, right, at least a brief. So now the question is, how you are really going to map, let's say, circuits to the FPGA. So now I would say that of course we will use a kind of a Vivado and the tools called, right? Okay, now what are the kind of the tools or the steps in Vivado, right? The first step is something called translate. Okay, so basically your Verilog design or whatever, right, it's going to be kind of translated into some kind of a synthesizable circuit, right? So that's what I have shown before. Now then that circuit has to be kind of a map to your LUTs. So now given of course FPGA contains what? LUTs, right? LUTs and all, your circuit has to be really mapped into the LUTs. In an ASIC design, the synthesis means you have AND gates and OR gates. So given Verilog design, it has to be mapped into given gates. But here in the FPGA, what we have? We have LUTs and all. So given the Verilog circuit, so from there I am generating a generic description. Now that description has to be really finally mapped to LUTs. And if somebody had a kind of an experience of looking at the netlist generated by Vivado, you might have seen just it's instantiated many LUTs. So after that, what we have to do is that, so we have to do the kind of a place and route, and then of course we have to check the timing, and then we have to generate the bit file. If everything is fine, so it will generate the bit file, and then we have to program it. So here I am just trying to explain one example. So here, so we have a kind of a piece of code. Okay, so always at the passage of clock, or the negate of reset. So if not reset, so right, so we have a q equal to 0, basically it's a active low reset, and of course right, so the clock pin is nothing but clock signal is nothing but CLO CK, and then of course so the q is nothing but your q, right. So the q output of D flip flop will be connected to a signal called q. Don't get confused. Okay. So now, so this is a generic description, right. So we have this A CB which is implemented here, we have a BD and we are Ring and is connected to D input. Okay, now here if you see, right, this is our general description, right. But now, so how do we really implement this general description, right, or generic description? So we have to use an LUT. Okay, now, so here we are assuming that we have an let's say we have an LUT of 4 inputs. So that's the reason we are using only single LUT. But of course, if we do not have a LUT of 4 inputs, we have a LUT of 3 inputs. We will use multiple inputs of multiple LUTs of the same thing. So this is what kind of the first step was, right. So translate. This is a translate step and this is a mapping step. Okay. So now here in this slide, so one such circuit is again shown, right. So we have a different circuit now. Okay. So now we are trying to really kind of map the combination logic into different LUTs. Okay, different colors denote the different, let's say, LUTs. So we are trying to really map. Okay. So once this mapping is done, okay, now on the physical, right, the FPGA we have the CLB slices. Now we have to really choose it. Okay. So where this LUT is going to be used. So it looks like, so maybe in the CLB, right, maybe we have 2 LUTs in each slice, or maybe in each, of course we have many slices, and each slice maybe you have 2 LUTs, right. So now let's I decide that, okay, these 2 LUTs will go here. Okay. So these 2 will go into the next one. Okay. And of course, right, these 2 will go here and the rest will go here. So now when I am trying to really kind of do this placement, so right, I should also be timing aware. Okay. So I also need to really make sure that which is connected to what, and make sure that the routing is really feasible. Okay. So in the next step what we'll do, right. So the like in ASIC synthesis and all, or ASIC placement and routing, it's everything is also here the timing driven placement. We have to really make sure that what is an optimal placement for a given LUT and all. Again, there are algorithms which can do that. So basically, right, so you do the placement and do the routing. So right, once you do the routing, let's say the timing is clear. So what you do is that you will generate a bit file. Okay. So now I just said, right, so the bit file, what does it contain, right. So basically, right, the bit file will contain the programming data for your LUTs and the programming data for your interconnect. Okay. So far what you have done is that the mapping of a circuit means basically we mapped, let's say, given Verilog code to the gates, and from gates to LUTs, and of course, right, if there is a memory, right, so we can also map it to block, let's say block RAMs, and if there are some multiplications and all, we can also map it to the DSP slices. So this everything is really taken care in the software tools. Okay. Now to the end, so what we need to do is, but we need a way of configuring the FPGA, right. So here what does it mean by the configuration is that how to store the truth tables of each LUT, right, and then how to connect the wires between. Okay. Now if you look at this bit file, right, so that's what it has, the configuration for your LUTs and the programming data for your switches. Okay. Now so okay, in a typical FPGA, right, so we have too many, let's say, LUTs and too many, let's say, the switches. So how do you really program each bit? Okay. So now I think Steve sir mentioned about something DFT, right, so scan chains and all, right. So here also what we need to do is that we have to connect all these, let's say, CLBs in a one kind of a chain fashion. Okay. Now let's say for each LUT you wanted to program directly. So now I mean to say that, okay, now the CLB we had, right, we had 2 slices, right. So how many input we had? Let's say we'll only talk about only one slice. We have F4 inputs, G4 inputs, right. Now you wanted to program exactly the content into that, right. So we need a direct pins, right. Okay. Now from each such CLB you wanted to take the pins and connect it to the FPGA, right. So we have so many CLBs, and if you bring out all those, let's say, pins to the outside the FPGA, right, the pin number will really explode, right. So now what we need to do is that, so right, all these CLBs, right, so we have to make some kind of a, let's say, kind of a chain, something similar to the scan chain. So here all the memories are really connected in a shift register fashion. So now in the shift register what will happen? You give one input to each clock and then it shift it, right. Let us assume that, okay, for the time being let us assume that each CLB is one flip flop, right. Now what we have is total, how many we have? Total 12 flip flop we have, right. So we have 4, 4, 8 and 12, right. So now I wanted to program, let us say this down CLB with a 1, right. I will start my input stream with a 1, I will shift it, right, and then this I wanted to store 0, right. So I will 0 and again shift it, okay. Now after let us say 12 cycles I will exactly have the content which I wanted to have, right. So now what is the advantage with this? With this is that now if I wanted to connect each CLB to out, I need 12 pins for the FPGA, right. But in this case with a single pin I was able to kind of push the data in, okay. This is the same concept which we use in the scan chains, okay. Now once these let us say CLBs are connected in a kind of shift register fashion, we can simply put send the bit file and then of course each clock cycle will bit in, let us say kind of shift in. So now after the bit file is kind of completely programmed, that means each LUT will get exactly what is supposed to get and each switch matrix will get it's a programming bit, it's 0 or 1 or whatever it is, okay. So that's what we are trying to really show in this next slide, okay. Again we are just again showing a very simple example. So now, so this is a simple full adder circuit and now we wanted to let us say generate a bit file, okay. Now it's a simple let us say combination circuit, right. So now what should the let us say bit file should contain? So this is the content, right, okay. Now let us say this is your LUT. So after the programming, so the content should be exactly something like this, right, okay. Now and now so here so we have a flip flop and we have a multiplexer, right. So now do you want to really kind of take the input through the flip flop or bypass the flip flop? Bypass, right. So that means let us say the multiplexer 0 pin is combinational output and the 1 pin is your let us say I think so vice versa I guess, 0 is your flip flop, 1 is your combinational let us output. So basically what do you expect? This multiplexer should be really programmed with 1 and the rest of the content should be here. So what you do is that you generate let us say the bit file, I mean the the truth table content. What you do is that each cycle you just shift in, so 1 bit by 1 bit, right, okay. So right, so basically right, so these 8 bits including this one, but now this is a simple example, right, but in a real FPGA, right, we have so many that CLBs and all those things, right. So I mean they are connected in a fashion and now that is the reason, right, many of the people, right, I mean when you are configuring your Vivada project you don't select the right FPGA. So the bit file will generated and now the bit file the tool doesn't understand. So that is the reason it's very important that when you are let us say working with FPGA, which FPGA you wanted to really choose, right, that you have to really select it. So now the tool knows that okay how big is your FPGA and what are the CLBs and everything it knows and then it will generate the bit file correctly, okay. Good, I think that's all I have I guess, okay. So one disclaimer is that I don't really own all the slides, so they are copied shamelessly from all the different resources, and these are some of the references which I used and actually this is the content which I always use for the ADSD course, but I just try to kind of fit it to this 2.5 hours lecture, okay. So now with this, so I don't have any other content, but if you have any questions with respect to those let us say sheets which are distributed, we can discuss, okay. Okay, so we are done for the day, but we can just sit and discuss the questions which we have.